Hey guys. Okay, so this is another problem by Professor Spilio. So we have a yo-yo with a no slip condition. The yo-yo is released downwards and the yo-yo has mass m and radius r, and we're trying to find ACM in terms of g. So we're treating this like kind of an old-timey yo-yo where the radius is where the string is coming off on the outside, so it's not like at a smaller radius. Um, Otherwise, our equation for torque, the radius for our torque equation, wouldn't match the radius for our mass moment of inertia. We'd have like two different radiuses, which would be fine if we had values, but solving symbolically, it's going to make things a little bit uglier. So the radius that the torque is acting on is going to be the same radius for the mass moment of inertia, just the radius of the circle for this problem. Okay, um, all right, so we're going to approach this systematically. We also know that we have a no slip condition. So when we have a no slip condition, we're going to apply the same things that we did for question number 1, okay? So we know a couple of things, okay? I'll take this. We'll do this on our own here. So we know that the acceleration of the center of the mass for the yo-yo, so this is ACM, right, coming down, is going to be equal to this r alpha, okay? So the radius times the angular acceleration, okay, um, of this yo-yo. So this, if the tension is pulling this way, the angular acceleration is going this way, right? So the yo-yo is spinning this way. Okay, so, and this is our A, this would be ACM. I don't know why I read it twice here. Okay, so we know that when we have this object spinning, so we have this A tangent, right, is equal to this ACM is equal to this A tangent. So the rate that it's spinning, if it's moving along a surface, this ACM would be equal to this A tangent. One or both of these, or one of these may not exist, but that still would mean that the other one is still equal to this R alpha, okay? All right, so the way we're going to do this to find ACM is we're going to start with our sum of forces equations, okay? Or we're going to start with 1, just systematically, free body diagram. 2, sum of forces and sum of torques, okay? 3, what else? Like other relationships, other equations, and knowns. Just basically anything else. And then 4 is algebra. Okay, so let's go ahead and start with that. So 1, let's do our free body diagram. So the yo-yo itself is just a circle, right? And we have the weight of the yo-yo acting from the center of mass, right? So this is mg, and then we have some tension, right? And we're given kind of that in our drawing over here. Now, what are we going to do next? We are going to look at our sum of forces equations. Okay, so we just have one object, okay? So we're going to look at sum of forces, right? And the x would be 0, sum of forces, and the y would be equal to t minus mg. And we want to ask ourselves, like, is this going to be equal to some acceleration? And in this case, yes, because the yo-yo itself is falling, right? So there is going to be the mass, right, times some ACM as the yo-yo itself is falling, right? So there is some acceleration. Okay. Then we are going to look at, all right, so we have our sum of forces, and then we have our sum of torques. Okay, so in this case, we have tension that's acting, right, at some r distance away, r, and the base of our tension is here, right, it's along the yo-yo, and this is our angle. So we know that our mg force would not be causing a torque because the radius, the distance that it is from the center of mass, the base of the force, is 0. So we would have 0 for that one. And then for this tension, this would cause a negative torque, right? Because I'm actually sorry, this would cause a positive torque because we're going in the counterclockwise direction. So positive torque. And so we have, this is going to be equal to r, right? Or r of our circle times t sine of 90 degrees, which is just going to be equal to rt. And that's going to be equal to I alpha. And we know that this alpha exists because we do have some angular acceleration. This object is rotating. And so, yeah, those are our equations to start out with. So let's see if I can get through this before my pencil dies. Okay, so far so good. All right, we got everything set up. So we're trying to solve for this ACM. we're going to use this no slip relationship, right? Where so long as there's no slip, the rate at which this is like unraveling is going to be equal to or the acceleration at which this is like unraveling is going to be equal to the acceleration that it's falling with, which is going to be equal to r alpha. So let's say what we're trying to find. So ACM is equal to r alpha, and we're going to sub in this alpha for ACM over r. Okay, so this is our next step. This would be 3, where we're using our other relationships, right? We also know our mass moment of inertia because it was given to us by the problem, right? We also have I is equal to 1/2 mr squared, so we can use that one as well, okay, when we're approaching this problem. And I think that should hopefully be all we need. So let's plug in everything and try to solve for this ACM. Okay, so we're going to start with this equation. I'm going to call this 1, I'm going to call this 2, 3, 4. Okay, so we're gonna use equation 3 first, and then we're gonna sub in 4 and 2. Okay, so equation 3, so we have RT is equal to I alpha. Okay, and so we're gonna sub in our ACM for R alpha. For this one, because our yo-yo is moving in like this negative direction, we're going down. We're going to model this. So VCMX in the negative y direction. Um, so we're going to plug in a negative ACM for this guy. Okay. So we're going to plug in I times, let's see, negative ACM over R. So, and then our I is equal to 1/2 mr squared times negative ACM over R. Okay, so we're going to cancel out these r's here. We're going to have 1/2 mr ACM. It's going to be a negative. Okay, so we also have another r on this side, so we're just going to cancel out these two. So we're going to have t is equal to negative 1/2 ma. It's looking very similar to our last problem. So we can say negative t is equal to 1/2 ma. Okay, so far so good here. Okay, so our ACM is down. Now we want to use our other equation. We're going to use equation 1. So we have t minus mg equals m times ACM. So this should look very familiar. So negative t, we're just going to add this one again. Negative t equals 1/2 ma ACM. So this is ACM. Sorry, I think I dropped that subscript at some point. Okay, so I'm going to put that one into our equation here. And, okay, 1/2 MACM, right, plus MACM. Okay, so plugged everything in here. So we have 1/2, right, 1/2, well, sorry, let me do each side of the equation here so I don't confuse myself. So we have negative mg because we added these two negative tensions, right? And this is going to be equal to MACM, right, plus 1/2 MACM. Okay, so M plus 1/2 M, right, times ACM. So just combining the masses, right? So we had an M here and a 1/2 M here, and these two are our ACM values, right? Equals mg. Okay, so I'm going to divide everything by m, right? So I'm going to have negative g is equal to 1 plus 1/2, because I just basically multiplied everything times 1 over m, right, on both sides, right? Okay, and that's equal to ACM. So I have ACM, so this is 1/2 plus 1 is equal to 3/2. Okay, ACM. So negative 2/3 g is equal to ACM. Okay, and that's the acceleration of the center of mass for this yo-yo. So as this yo-yo is falling, the acceleration of its center of mass is equal to negative 2/3 g.